Okay, so in today's expressions section, we are going to focus on the domain, and we're going to be able to determine the domain of a rational expression and we are going to do something that is going to feel wrong. It's going to go against what your math teachers have been telling you for a while. We are going to rationalize the numerator. So I know you've been told, hey, rationalize the denominator, rationalize the denominator. Yes, you do want to rationalize the denominator when you are simplifying. That is the proper form. But there are applications for rationalizing the numerator. We're going to talk about it more at the end of the year when we start to preview calculus. It has to do with finding limits. But today we're going to start talking about the algebra behind that. Okay, so when we are focusing on the domain, we have to remember that some algebraic expressions might not be defined for all values. Okay, if it is defined, we would just say all real numbers. The domain of an algebraic expression is the set of real numbers, so not imaginary. Okay, it's the set of real numbers that the variable is permitted to have. So we're going to go over this table, but maybe you guys remember a few things we had to watch out for last year. So last year we were always checking for two things, right? What type of situations do you get something that's undefined? What are things you can't do? Yep, so you can't have a negative under an even root. That's one of the ones we're going to do. The first one is probably the most common. It's probably one of the first indeterminate things that you learn, right? With fractions, what can you have with a fraction? Yes, Lucas, in words. What can you do? Yeah, you can't divide it by 0, right? So if you have 1 over a variable, we know that the domain would have to be x such that x cannot be 0. And I'm going to kind of jump down here as we talk about this, because it says, do the domains make sense for each expression based on past algebraic properties you studied? Yes. So for fractions, you can't divide by 0. That's where it comes from. So when we're solving, we know the denominator can't be 0. We're going to use that to help us solve. And with an even root, you can't take an even root of a negative. So we would say x such that, so does it include 0 or does it not include 0? Can you take the square root of 0? Can you take the square root of 0? Can we try it? You have a calculator. Really, when you take the square root of something, it's just because a number times another number is that value. So can you multiply something by itself to get 0? Yeah, 0 times 0 is 0, so the square root of 0 is 0. Okay, so it is going to include 0. Okay, and then with even roots, you can't take an even root of a negative. This shows a square root. It's true for all even roots. So even if you wanted to put like the nth root, or sorry, I guess I should have used x, where n is an even value. Okay, Doesn't matter for odd roots because you can take an odd root of a negative. Okay, the last one combines the two. So if you have 1 over the square root of x, we're combining these two together. So if x can't be 0, but it has to be greater than or equal to 0, how would we say that? It has to be greater than or equal to 0, but it can't equal 0. Yep, it would just be x is greater than 0. So when you combine those two together, that's when you get rid of the equal to. Okay, so if you have an even root in the denominator, that's when we're going to use this. Okay, so we are going to find domains for the following expressions. And when we're doing the domains, we're going to write them in both set builder and interval notation. Okay, so we're going to use set builder and interval notation. Okay, your quiz will ask for both as well. So when you're practicing, you're going to want to practice both. Okay, so for part A, we have the square root of x plus 5 over x minus 2. Starting off with a doozy here. Because we have a few different things. So the first thing I always ask myself, is there a fraction? Okay, if you have a fraction, which we do, we know the denominator can't equal 0. Okay, so the first thing I ask myself, is there a fraction? Okay, yes. So then we are going to set the denominator equal to 0, and we're going to solve. Okay, because we know the denominator cannot equal 0. So if we have x minus 2 in the denominator, we set that equal to 0, we're of course going to get x equals 2, and then we know it can't equal 2 because the denominator can never be equivalent to 0. So we're going to have to include that in our domain. Okay, the second thing is there an even root? Yes. Okay, so what we're going to do is we're going to take the radicand, and we have to set that greater than or equal to 0. Because whatever is underneath the radical has to be positive. So we can just take that number underneath, which is x plus 5, set that greater than or equal to 0, and then solve. Okay, so I'm going to move over the negative 5. Okay, so I have these two here. Okay, and then I have to combine those. So when you're doing them in set builder notation, you can just say x such that x is greater than or equal to negative 5 and x cannot be 2. You want to say the and because both of those happen at the same time. This is the quicker way to do it. You could also, I'll show you it on an interval. I'll show you another way you could do it. Okay, now what I think is helpful when I'm doing the interval notation is I like to visually see what this represents. Okay, so I have negative 5 and I have 2. So what this is saying is I have a closed circle at negative 5. It's all the values to the right, except if it can't be 2, there's an open circle here. Okay, so this is going to be one of my intervals. This is going to be my second interval. So when you're doing the interval notation, you're going to use brackets and parentheses. So if it's a closed circle, you have a bracket, and then it has to go to 2. With the 2, I have to use a parenthesis because it doesn't include 2 in there. Anytime you see an open circle like this, there's going to be a union, okay? A union between those 2 intervals. And then it picks back up at 2 and goes all the way to what? What does the arrow mean? Infinity. Yep. Okay, so I like seeing that. You don't have to draw it out on a number line. If you get better at this, then you might want to start doing it and then drop it. That is fine. Okay. And so the other way you could write it in Set Builder, which I think takes a little more work, would be x such that you could say that x is between 5 and 2 with an equal to and a less than, and then you would say or x is greater than 2. Okay, that would be an acceptable answer as well. I think this way is going to be a little bit quicker, and this is how your textbook gives you your solutions. So that's what I'm going to show you. All right, so we're still finding the domain. So for B, you have negative 5x squared minus 6x minus 6. So recall that I said I always ask myself 2 questions. My first question is there a fraction? Last time the answer was yes, this time the answer is no. Okay, then I'm going to ask myself, is there an even root? Again, the answer is going to be no. There are neither of those. So when that happens, your domain is what? All real numbers. Okay, so if those restrictions don't happen, okay, you're going to write all real numbers in set builder notation, which is just x, such that x is an element of the real number set, and an interval notation, which is negative infinity to infinity. Okay, do you guys remember doing things like this before with domain? Okay, and then for C, we have x squared minus 9 over x squared minus 6x plus 8. Okay, so ask yourself your 2 questions, and then let's see if we can set something up with one of those. Okay, so your first question is if there was a fraction, and there was, so if there's a fraction, your denominator cannot equal 0. Okay, so we're going to set this equal to 0 and solve. So to solve, you can factor. Okay, so what multiplies to 8 but adds to negative 6? Well, negative 4 and negative 2. Okay, so this will produce x is equal to 4. This is going to produce x equals 2. So it can't equal 4 and it can't equal 2. when you are doing your domain, when you are doing the set builder notation, you can just say x cannot be 4 and x cannot be 2. When you are doing the interval notation, again, you might find it handy to think of this on a number line. So we do have to put them in order here. So you have to put the 2 first and then the 4. So what this is saying is you have an open circle at 2, you have an open circle at 4, anything else is going to be a solution. So anything to the left here, any number in between, any value to the right. So can you see how many intervals it's broken up into there? 3. Okay, so if it's broken up into 3 intervals, okay, that's what we're going to have to do. So we're going to have 2 unions here. So this first interval here is going to be negative infinity up to 2. So we just write it like this, negative infinity to 2. And then we're going to join that with, it goes from 2 to 4. And then we're going to do 4 to infinity. Okay, so you can have more than one union, that is fine. Okay, it's going to happen when you have 2 excluded values there. All right, why don't you give part D a try? You can use your table to help you with that. And notice we didn't use the numerator at all. So it doesn't matter what the numerator is. The numerator can be 0. It's only the bottom that has the restriction. Set up. Okay, so this thing, when you're asking yourself if you have a fraction, yes, you also have a radical. So whenever you have a radical in the denominator, that is when you have to take the radicand and set it greater than 0. Okay, so it's very similar to what we do if the radical is in the numerator. It's just now it can't equal 0. So we're just going to take that 2x plus 3. We're going to set it greater than 0. So we're going to subtract the 3 over. We're going to divide by 2. Okay, and then we're just going to write that in our proper notation. So for set builder, it's just x such that x is greater than negative 3 over 2. And then whenever you're having trouble with intervals, just go back to this number line. If it's greater than, it's an open circle. And then it's everything to the right. So if it's an open circle, you have parentheses, negative 3 over 2. The arrow to the right means you're going to infinity. Okay, and then this one you have the square root of 6x over 5x minus 7. Okay, this is another one where you have a combination. So remember, when you have a fraction, we know the denominator can't be 0. Okay, so your work can be as simple as saying, okay, this can't be 0. So we're adding over the 7, we're dividing by 5. We know that x cannot be 7/5. Okay, so your denominator cannot be 0. Now, the numerator has a radical in it. So first step fraction, second step radical. Whenever you have a radical, if it's on the top and not on the bottom, it's greater than or equal to 0. So this is going to be part of it. The other part has to come from solving this inequality. Okay, so if I divide each side by 6, I have x is greater than or equal to 0, and then I have to combine those two together. So when you're doing that in set builder notation, you can just say x is greater than or equal to 0 and x cannot be 7/5. Okay, when you're doing this in interval notation, make sure you put these in order. So 0 would go here, 7/5 would come after. Anytime it can't include it, it's going to be an open circle. This is going to be a closed circle to the right. So if this breaks it up into 1, 2 intervals that you're going to have to label there. Okay, so if it's a closed circle, we have a bracket. So it starts at 0. It goes to 7/5. And then because it can't include 7/5, we use the parenthesis. And then it goes from 7/5 to infinity. Okay? What questions do you guys have for me on that? You need to make sure that that is in this order. You can't flip those around. Whenever you're doing the domain, you have to go from the lowest to the highest value. Okay, so you do need to keep that consistent. Okay, we are going to talk about conjugates because they are going to help us rationalize denominators and numerators. So these are going to be called complex conjugates, or really they're your conjugate radicals. So if a fraction has a denominator of the form a plus b root c, we can rationalize the denominator or the numerator by multiplying both the numerator and denominator by the conjugate radical of the form a minus b root c. Okay, the reason why this works is if you use this special product formula, and I took this right from your book, if you use this special product formula where you FOIL a plus b root c times a minus b root c, let's see what happens here. So if you were to FOIL, a times a is going to be a squared, yep. And then in the middle here, you'll get ab root c. It'll be a positive. On the outside here, you get negative ab root c. So those cancel out. And then when you multiply here, you have a positive and a negative, so it'll be negative. B times B is B squared. What's root C times root C? C. So this undoes the radicals. We don't have any more radicals in there. Okay, so I'm going to give you some complex values, and then I want you to just write down what their conjugates are. Okay, so the first one is 2 minus root 3. 2 is 5 plus 2 root 5. And 3 is negative 2 minus root 7. Okay, so 2 minus root 3, 5 plus 2 root 5, negative 2 minus root 7. Okay, so write those down and then I'll want you guys to help me. All right, Kyle, what'd you get for your first conjugate? Good. Okay, and then Solomon, what'd you get for your second one? 5, and then tell me what the second part was. So do the opposite of it. Nope, so instead of doing plus again, let's do the opposite. Yep. Yeah. Okay, so even if there's a number in front, we're just going to do the opposite there. And then you know what you put for 3. Okay, tell me what was different about that. Yeah, negative 2 plus root 7. Yeah, good. Okay, so the only thing that changes is going to be this middle value. So if it's positive, it'll be negative. But notice here, if this is A, this is A. So just because this is a negative, don't switch that. We didn't make this positive to negative, right? We kept those both positive. We kept those both positive. So it's going to be the same process here. All right. So in example 2, we're going to be rationalizing the denominator. Do you guys think you can do A without me, or do you want a little hint to get you started? So you're rationalizing the denominator, so you have to multiply the same thing by the top and the bottom. Okay, so if it's 1 minus root 7, Brooke, what are we going to multiply by for this? 1 plus root 7. Yep, over itself. And so in the denominator, you're going to FOIL. Okay, so why don't we work on FOILing the denominator there? Go ahead, you can try the next one. All right, so good simplification. Okay, so when you FOIL, you get the 1 times 1, which is 1. And then inside you get negative root 7. Outside you get positive root 7. Those are going to cancel out. And then negative root 7 times root 7 is negative 7. Okay, so you're going to end up with 1 minus 7 on the bottom, which is negative 6. Okay, and then on the top, we're just going to distribute. So we're going to have 12 plus 12 root 7. How did that go? And then I saw many of you did a nice job simplifying, right? Because negative 6 is going to go into both of those. So we're going to divide. 12 divided by negative 6 is negative 2. So it's negative 2 minus 2 root 7. That's going to be your final answer. Okay, and then here we're going to multiply by root 5 plus root x. So this is the conjugate. Okay, these stay the same. The value inside is going to change. Or sorry, the value on the outside here is going to change. So when you're multiplying, remember root 5 times root 5 is just going to be 5. This is the first term when you're doing FOIL. Okay, the inside terms are going to be negative root 5x and positive root 5x. When you multiply a root by a root, they both go underneath the root. Okay, so we know those are going to cancel, and then we can just worry about the first and the last here, okay, which is just going to be minus x. Okay, so root x times root x is x. A negative and a positive is going to make a negative. Okay, and then here we're just going to distribute. So you have x root 5 plus x root x. There's nothing else you need to simplify here, so you can leave it like that. Something you're going to notice is that there are equivalent forms. So sometimes if you're checking your answer with a key, you might have an equivalent form of the correct answer. So if the answer key like said x root 5 plus x root x, and instead they had this negative factored out, okay, that would be fine. Sometimes they even take this negative that they factored out and they apply it to the numerator. So they would distribute it to the top like this. Okay, this would be an equivalent form. So it's important that you can recognize those. Especially because this is a year a lot of you are going to take those standardized tests. You might solve it in one form, and one of the answers might be an equivalent form. Okay, so don't assume that you automatically did it wrong. See if there's an equivalent form that matches yours. Okay? All right, so now that we practiced rationalizing the denominator, we're going to rationalize the numerator. Okay, so what we're going to do is we're going to take the conjugate of the numerator, we're going to multiply that by both. Okay, I know some of you guys have already started that. Make sure you're checking in with me because this is going to be a little bit different. Okay, so the conjugate of the square root of 1 plus h minus 1. Whatever is inside the radical has to stay the same. So the conjugate is 1 plus h plus 1. Can you guys think about why that has to stay the same? Why 1 minus h wouldn't work? Yeah, because it's not the same term, and you need the same term in order for what to happen. And you need it in order for it to cancel out with your square root, right? Because if you have 1 plus h squared, that undoes the square root. Okay, if you didn't have it, it would not undo that. Okay, so when you are doing this, you are going to FOIL or multiply the numerator. And FOIL is just the same thing as multiplying. Okay, so you're going to FOIL the binomials there, but you are not going to distribute in the denominator. Okay, so do not distribute when you're multiplying in the denominator. Okay, you'll see why in a few moments. Okay, we are going to be manipulating this equation a little bit. Okay, so let's FOIL the numerator, and then we're going to keep the denominator as h multiplied by a quantity. Okay, so we're going to multiply the first term by the first term. So root 1 plus h times root 1 plus h is going to give us 1 plus h. Okay, and then negative root 1 plus h, positive root 1 plus h will cancel. Negative times a positive is a negative. And then we're going to keep this as multiplication for right now. Now we look at the top and we see that we have a cancellation. 1 minus 1 is going to cancel. So we have h over h times 1 plus h plus 1. Okay, now you're going to notice, hey, if I have h divided by h, what does that make? This makes 1, right? So then your final answer is 1 divided by the root of 1 plus h plus 1. That's going to be your final answer. Okay, for part B, you have these two roots multiplied together. We're going to change those. Yeah, question this one. So if you distribute it, it's just a little bit harder to see that you're going to cancel out. So if you have it on the outside, you just cancel those. You could still recognize it if you did. It's just as your factors get more complicated, you're going to want it on the outside. And that'll be one less step too. Okay, so when you are rationalizing a numerator and you don't see a fraction, just remember that this is over 1. Now it's a fraction. Okay, so this is going to be your numerator. Okay, when you have the square roots multiplied together, keep in mind this just means the square root of x times x plus h. Okay, so if we distribute that, this is the same thing as x squared plus xh, or you could write hx. Either one is fine. Okay, so that's going to make it a little bit easier. So when you multiply by the conjugate, you can just multiply by the square root of x squared plus xh minus the square root of x plus 1. And then whatever you multiply by the top, you have to do the same thing to the bottom. Okay, so let's FOIL the numerator and see what happens. First term by first term. Okay, so when you multiply any root by itself, you're just left with that value underneath. Okay, the inside and the outside should cancel. And then root x plus 1 times x plus 1 is x plus 1, but be careful here. This is a binomial. Whenever you have a binomial, I recommend putting it in parentheses so you remember to distribute. Okay, that's something that's really easy to forget. We're just going to keep this the same for right now so we don't have to write that out every single time. And then we're going to distribute the negative here. So we have x squared Like I said, you can write this as xh or you can write it as hx minus x minus 1. Okay, and we do need to make sure that's distributed. And then this is x squared plus xh minus x plus 1. Okay, so based on that, why don't you guys try part C? So when you're multiplying, just remember any root any root multiplied by itself is going to be that radicand, and then root y times root y is going to be y, and then they're opposite, so it'll be a negative. Okay, and then the y's will cancel, so you'll have negative 6 divided by the square root of y minus 6 minus the square root of y. Okay, and that's going to be your final answer there. Okay. All right, and then this is your second set of color columns from 1.4.